So, hello, and in this one, as we have talked about, we are going to continue the problem from the last video. So, let me just give a brief overview and write down the whole problem again and write down what progress we have made so far. So, f of x comma y comma z is basically x to the power y, and it was a big function which we had done earlier, but I'm going to also do it in this one so you would know what to do. X into sine of y sine z. Okay, and what we understood from this was that obviously even you were to make sure that this function has two variable limits, it wasn't really much of a deal to connect these dots to the fundamental theorem of integral calculus, because it basically said us that we need to have the derivatives of these two functions, right? So I'll write down the rest. Now, df of a comma b comma c was basically equal to, as I said before, if we call this function as h1 of x comma y comma z and this function as h2 of x comma y comma z, then we can write this as minus and we only need to find dh1 abc and dh2 abc. So let us actually start by the simpler one, that is dh2 abc. So h2 of x comma y comma z is simply x to the power y, which is e to the power y ln x. This can be written as exponential of y log x, right? Therefore dh2 at the point abc therefore this would give us the derivative of exponential function is basically exponential itself, so that is not a problem. This becomes exponential of b log a. Now this derivative would be pi 2 prime into ln of pi 1 at the point abc plus pi 2 into ln of pi 1 prime at the point abc, right? So this can be evaluated because we know that the derivative of log x is just uh, log of some function f of x is basically f dash x by fx. So we can do this as follows. This is basically e to the power b log a multiplied by pi 2 prime is 0 comma 1 comma 0. Log of pi 1 at the point ABC is basically ln of a. Now pi 2 at the point this is basically b. Ln of pi 1 whole derivative is basically pi 1 prime by pi 1 divided by pi 1 means a, and pi 1 prime means 1 comma 0 comma 0, right? So this becomes a to the power b, and this becomes therefore putting in all the values we get which is the derivative for dh2. Now comes the part for dh1. So remember, recall the function dh1 first. h1 of xyz was basically equal to sine of x sine of y sine z. Okay, and this basically can be written like this: sine of x g of y comma z, right? So what we are going to do here is something like this, that we're trying to evaluate this integral one by one, and we're trying to do it in parts. So this can be written as sine, and you're going to have the function x sine y sine z, and let us name this function as p1 of x comma y comma z. Then we can see that dh1 at the point a comma b comma c is simply derivative of sine at the point p1 of abc multiplied by p1's derivative at the point abc, right? So this is basically our thing. So this becomes cosine of p1 abc multiplied by dp1 at the point abc. Okay, so this is basically it. Now we need to find out the derivative of p1. So recall again that p1 of x comma y comma z is simply x multiplied by sine of y sine z. Therefore dp1 at the point abc would just be the derivative of x, which is basically 1 multiplied by this. So we have derivative of x at the point abc multiplied by sine of b sine c, right? And plus we have this thing. So this x basically is pi 1 here. So it basically is pi 1 multiplied by derivative of sine of y sine z at the point ABC. Okay, so this becomes pi 1 prime into sine of b sine c plus pi 1 into sine of, you can write this as pi 2 sine c derivative at the point a comma b comma c, right? So let us consider this function as, let's say, p of 2 x comma y comma z. Let us find the derivative of that first. Given p2 of x comma y comma z is sine of y sine z. Remember that we are taking three variables as input because that's what the whole function is about, and this can be written as sines composition with pi 2 sine pi 3. Okay, therefore dp2 at the point ABC is simply equal to derivative of sine at the point ABC plus not plus, actually, multiplied by pi 2 sine of pi 3 derivative at the point ABC. Now the derivative of sine is basically cosine, so it becomes cosine of b sine c, and multiplied by this becomes, now pi 2's derivative is pi 2 derivative. Pi 2 sine pi 3 can be evaluated by the rule of product, which is pi 2 derivative times sine of pi 3 at the point ABC plus pi 2 into cosine of pi 3 into pi 3 derivative at the point ABC. Okay, so this becomes cosine of b sine c multiplied by, now pi 2's derivative is simply 0 comma 1 comma 0, and sine pi 3 at the point will become just sine c, plus pi 2 cos pi 3 is basically b cos c, and the derivative is 0 comma 0 comma 1, right? So this becomes cosine of b sine c multiplied by 0 comma sine c comma 0 plus 0 comma 0 comma b cosine of c. Okay, now since the vectors can be added together, what we can do is cosine of b sine c, and the vectors are basically 0 comma sine c comma b cos c. Okay, so that's basically dp2. So therefore dp1 abc can then be written as, so let us check what it was, pi 1 prime into sine of b sine c, so it's basically is pi 1 prime means 1 comma 0 comma 0 multiplied by sine of b sine c, sine of b sine c. Okay, and then we have this, then we have pi 1, which is basically a, cosine of b sine c times 0 comma sine c comma b cos c. Okay, so all in all what it gives us is this sine of b sine c comma a into sine c into cosine of b sine c, and at the end it gives a b cosine of c into cosine of b sine c, and this is what dp1 is basically all about. Now if you remember, dp1 was basically this, and we had that p1 abc was this, so dh1, which is what we wanted to find, is basically cosine of this x sin y sin z at the point abc multiplied by the derivative of p1, right? So therefore So therefore dh1 at the point ABC is simply cosine of this. Okay, so it's basically cosine C multiplied by dp1 of ABC, which is now known, and we also know that dh2 of ABC is simply a to the power b minus 1 b a to the power b log a comma 0, right? Therefore df of a b c is simply equals to, now we understood the function and we can now find out that this is simply equals to sine of a sine of b sine c multiplied by dh1 of a comma b comma c minus g of a to the power b multiplied by dh2 of a comma b comma c, which is the answer. And dh1 and dh2 are as defined above, and dp1 is also defined above, so you can find the derivative at basically any point where it is defined, right? So this is the type of problems that one should expect when we are calculating tough kind of derivatives. But then again, these derivatives are not so much into the properties and stuff, so yes, you can basically find out how to deal with them. So let us do another one now. And after this we shall move on to partial derivatives. X to the power y plus z. So we have f of x comma y comma z equals to y plus z. Basically we need to write this whole in exponential, so there won't be much space left if I were to do it there. So let us write it at like this: exponentials composition of pi 2 plus pi 3 ln of pi 1 at the point x comma y comma z. So this is how we can write this function f in composition form, and what we can do is this. Therefore, by the chain rule, we can see df of a comma b comma c is basically equal to derivative of exponential function at the point ABC multiplied by the derivative of pi 2 plus pi 3 ln of pi 1 at the point ABC. Now the derivative of exponential is basically exponential, and at the point pi 2 plus pi 3 whole into ln of pi 1, if you put it in the point a comma b comma c, it just becomes b plus c ln of a, right? It's basically exponential of b plus c ln of a. And now we have this derivative where we can see that it's just the derivative of pi 2 ln of pi 1 plus pi 3 ln of pi 1 at the point a comma b comma c. This means that exponential of b plus c log a is simply a to the power b plus c. And now this derivative, this is basically pi 2 prime ln of pi 1 at the point a comma b comma c plus pi 2 by pi 1 into pi 1 prime at the point a comma b comma c plus pi 3 prime ln of pi 1 at the point a comma b comma c plus pi 3 by pi 1 into pi 1 prime a comma b comma c. And evaluating this, we get, therefore we can write it in a new line, therefore df of a comma b comma c is equal to a to the power b plus c. And now pi 2 prime is simply 0 comma 1 comma 0, and ln of pi 1 is ln of a plus b by a into 1 comma 0 comma 0 plus ln of a into we have pi 3 prime, which is 0 comma 0 comma 1 plus c by a into 1 comma 0 comma 0, right? This would give us a to the power b plus c 0 comma ln of a comma 0 plus b by a comma 0 comma 0 plus 0 comma 0 comma ln of a plus c by a comma 0 comma 0. And therefore this means that this is equals to a to the power b plus c. Now 0 plus b by a plus c by a, so this becomes b plus c by a in the first quadrant, ln a plus nothing, so only ln a in the second quadrant, and ln a in the third quadrant. So we multiply together to get this. The answer is b plus c into a to the power b plus c minus 1 a to the power b plus c ln of a and a to the power b plus c ln of a, which is the answer. And if you check carefully, all of these three functions that you have found out are basically the partial derivatives with respect to a, b and c, which is very intriguing and an interesting fact here, because this kind of similarities do not often usually appear, but when they do, it's basically because we need to understand the importance that if a function's derivative exists, then so does its partial derivatives, because this multidimensional functions, they're composed of partial derivatives only, so all its component functions must also exist, right? So anyway, the added video with this would be about the derivative section, where we use the chain rule and stuff, and we can use them in order to find all different kinds of functions. So that will be added with it. Also in the next one we shall start continuing about all the properties and all the functions of partial derivatives as well. The derivative of a function f of x at x equals to a is given by f dash of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So what are the derivatives that we are going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sin b cos a. So this is the formula, right? So using this formula, we can see that sin of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a f dash a is equals to limit h tends to 0 sin a cos h plus sin h cos a minus sin a divided by h, right? So what we can do is limit h tends to 0 sin h by h into cos a. So we can just take the second term here and we can take the first term common and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one, sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sin square 2 by theta. So using that formula it becomes minus 2 sin square h by 2 by h, and this limit goes to 0, because firstly sin h by, if it was sin h by 2 we could have found the answer, but since it is sin square h by 2 it goes to 0. So the answer is cos of a. So the derivative of sin of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows: f dash a would be equals to limit x tends to a f of x minus f of a by x minus a, from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula. Now trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula what we can do is as follows. Using this we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of a into 1, because this limit is 1 as we have done in previous examples. So the answer becomes minus sine of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: f h tends to 0, f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common, as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1, as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down. List of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. is a to the power x. Number 5. Number 6. of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should actually work pretty well. So let me write down some more rules. some more rules. If fx and gx are two differentiable functions, then ddx of fx plus gx is equals to ddx of fx plus ddx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if you are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart. Let us begin with the chain rule. The chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dashed of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, It's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of. So we are going to do a bunch of problems now. So let us do d dx of e to the power ax. So d dx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now what is the most basic representation? It's e to the power x. So if you remember, d dx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down. But then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be d dx of ax, where a is just a constant, and when you do a constant x, a times x, the d dx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because d dx of x is just 1, and also d dx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. d dx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the d dx of ln of x is, because the first function is ln of x, right? So d dx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x and we write the derivative as 1 by x square. So do not directly write 1 by x because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into d dx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate d dx of log of sin x. Now how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now the answer can be written directly if we have that in mind, because we differentiate one by one and we keep on doing that until we reach the inner bottom where x is present. So d dx of log of sin x is simply equal to, firstly we do the d dx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see, we have got the answer. d dx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. we need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it was the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 of the is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.